Welcome to the course Basics of Materials Engineering. I'm your TA Alka Jankar from IIT Kanpur. In week 5, we'll be studying about failure of materials. So, this course is offered by Professor Ratna Kumar from Department of Mechanical Engineering, IIT Madras. So, firstly, we'll be going through some sample assignment questions. Then, we'll be going through some notes, which will be helping you in solving your assignments. So first question is, what doesn't act as a notch? So notch is what? It acts as a stress concentration point in your design, in your material design. So your options are a groove, smooth contour, hole or fillet. Your answer will be smooth contour because it won't be increasing your stress concentration. So in these are two different designs shown here. So in this, these are smoothened out, so there will be less stress concentration at these points compared to this square type of shape. So these below folds act as notches providing stress concentration. So a hole in, for example, will be using nut bolts. In that case, hole acts as stress concentration point. A groove, a fillet, an abrupt change in cross section such as here. In this case, cross section is changing relatively less abruptly. Any disruption to the smooth contours of the part, these all will be counted as notches, which can lead to initiation of crack in your material. Second question is,
Ma'am, I
yeah,
have a doubt in first one. Ma'am,
okay.
like con- uh, contour means मतलब होता क्या है वो exactly? What does it mean?
Contour is your any, like your this periphery that you are telling. In case of this periphery, these all are contours, so it should be smooth here. If this is smooth, then these stress lines that are shown here, right, these lines won't be concentrated at a particular point, which won't be increasing your stress concentration.
Okay, ma'am. Okay.
Now second question is, to apply fracture criteria, blank is used. Your options are fatigue strength, ultimate tensile strength, yield strength and creep strength. So your answer will be ultimate strength. So in notes also you may have studied that for applying fracture criteria we'll be using ultimate tensile strength. So the resistance of a material to yielding means it will start showing some plastic deformation, that will be given by yield strength. And to apply fracture criteria we'll be using ultimate tensile strength. And fatigue strength is your highest stress that a material can withstand for a given number of cycles without breaking. In this case we'll be using a cyclic type of loading. And in case of creep strength, it is defined as the maximum stress in a material that will result in a specified amount of creep in a given amount at a constant temperature. Second question is, at a certain point in structural member, there are perpendicular stresses 80 Newton per mm square and 20 Newton per mm square. Now both tensile, what is the equivalent stress in simple tension according to maximum principal strain theory, where Poisson's ratio is given as 0.25. Your options are 25, 50, 75 and 100. Answer will be 75, and this is the formula that you have to use. So in case of Hooke's law in generalized form, these strains, equivalent strain will be equals to E1. So E can be given in form of stress. So equivalent stress divided by capital E is your elastic modulus. So in terms of your Poisson's ratio, this formula can again be rewritten as sigma 1 upon capital E minus mu sigma 2 upon E. Now putting the values of sigma 1 and sigma 1 we have to take the higher one. So 80 minus 0.25 times 20. So this will be 5 and 80 minus 5 will be 75 Newton per mm square or 75 MPa. Now in fourth question, in the Hall page model, hardness increases with a reduction in grain size because grain boundaries. Your options are act as a source of dislocations, aid dislocation motion, act as barrier to the dislocation motion, or act as a sink for dislocations. So your answer will be act as a barrier to dislocation motion. So in case of Hall page relation, what we see that as we keep on reducing the size of grains, your strength will increase, strength and hardness. So for that, your dislocation need to act as barrier. This is your polycrystalline material. So these are the grain boundaries. So these will act as barriers for the dislocation moment. So a fine grained material, one that has smaller grains, is harder and stronger than a coarse grained, and due to the greater total grain boundary area to restrict dislocation motions. And grain boundaries also act as source and sinks of dislocations, but that is not the reason for hardness enhancement in the metals. Question 5 is the maximum distortion energy theory is suitable for which type of materials? Your options are ceramics, ductile metals, composites and polymers. So this theory is mainly used for ductile metals. And we can explain this by saying that maximum strain energy theory doesn't work on brittle materials because they have different elastic limit stress in compression and tension. And according to this theory, a body complex stress fails when the total strain energy at a elastic limit is in simple tension. And by using these formulas also in maximum strain energy, these are the conditions that I used. So in yield stress is used, and these your principal stress is sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu. Mu is your Poisson's ratio, and brackets sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. This should be lesser or equal to sigma y square for no failure. And we use some factor of safety in it in the formula for providing for so that our material doesn't fail. Now, which theory is suitable for brittle materials? Your options are maximum principal stress theory, maximum shear stress theory, total strain energy theory, and maximum distortion energy theory. Your answer will be maximum principal stress theory. So in case of brittle materials, maximum principal stress theory given by Rankine and stated as Rankine criteria is used, and maximum shear stress theory using Tresca theory, total strain energy theory, maximum distortion energy theory using von Mises criteria. These are useful for ductile materials. Tresca theory fails in the hydrostatic state of stresses, and all theories will give same result when the loading is of uniaxial type of loading. Now 7th question is two different stress state at a point in a ductile material are given at sigma 1 and sigma 2. Which of the following statement is true? Now one has 12, 13, 14 as principal, and sigma 2 has 17, 18, 19. Now sigma 1 is close to yielding, or the sigma 2 is close to yielding, or sigma 1 and sigma 2 both are equally probable for yielding, and sigma 2 is twice close to yielding compared to sigma 1. Your answer will be C, because this second sigma 2 can be written as sigma 1 plus 1 hydrostatic stress state. Now what happens if there is a hydrostatic type of stress state, then there will be only change in size of the or volume of the material, not there won't be any distortion. So second stress state is the addition of a hydrostatic stress state to the first. So both sigma 1 and sigma 2 are equally probable for yielding.
Ma'am, in the previous question,
Yeah.
like like some type of stress is being added to the first stress matrix,
Yes.
and then we are like producing the second one.
Yeah.
So like the second one will have like ma'am, more probability, no?
No, both will have same probability because we are using hydrostatic type of stress state, right? In this
Yes, ma'am.
case,
Like hydrostatic state of stress has no shear stress,
yeah.
but means what to say, ma'am? Like from what I understand is like if there is no shear stress, there is no distortion.
Yeah, so shear stress is same for both, right? The shear part of the stress is same 12, 13, 14, but we are just adding the hydrostatic part will just change the volume, it won't be leading to failure of material.
Okay, like ma'am, in both the matrices there is no shear component if we see it like.
No, there is shear part is there, but in both it is same.
Oh, okay, ma'am.
In 8th question, the uniaxial yield stress of a material is 866 MPa, and according to von Mises criteria, the shear yield stress of the material is 300, 400, 500 and 600. So in this case, using von Mises criteria, you have to calculate what shear yield stress will be for material. So it will be 500, and in this case in von Mises criteria, when we use uniaxial type of loading, then only sigma 1 and sigma 2 will be there in the formula, and all three will be equal. So sigma y tau will be equals to sigma y upon root 3. So now you just have to give the value of sigma y, which is 866 divided by root 3, which will be 500 MPa. Sigma y is your yield stress. Now, what is the shape of total strain energy theory? So there are various shapes provided to the various theories. So in that, your options are rhombus, ellipse, hexagon or circle. Answer will be ellipse. So these are various shapes that are given. So these are based on the equations that are given. So in case of your total strain energy theory, we can see that it is ellipse, and it is also ellipse for maximum distortion energy theory as well, which we'll be seeing after in when we'll be going through the notes. And in case of Tresca, it is hexagon, and in maximum principal strain theory, it is rhombus. Now question 10th, elastic limit of cast iron as compared to its ultimate breaking strength is half, double, thrice or same. So in case of cast iron, it is a brittle type of material. So what will happen, it shows very low amount of permanent deformation. So both elastic limit and ultimate breaking point, they both are almost same. So it will be similar. So in this case, it will be around here, breaking point will be around here for cast iron, So for brittle materials, stress strain curve looks different. Instead of having a clear yield point and plastic region, brittle materials often go from elastic deformation directly to the fracture, which means once the load exceeds a certain limit, the elastic limit, the material will fracture without any significant plastic deformation. Now we'll be going through some notes. So firstly, what is failure? So does failure mean the ultimate fracture, or how does one define failure for ductile and brittle materials? So in case of brittle materials, will be defining differently compared to brittle materials. And for engineering applications, what we consider as failure, so it will be depending on the what equipment we are using, what part of equipment is there, and are material properties important. So material important properties such as yield strength, UTS, fracture strength, these all also play important role. Now in case of fracture mechanics, we are more worried about the what is the stress state and what is the Craig geometry. Then these both of factors should overcome the material fracture toughness. And when we talk in terms of strength of material, then we say that as soon as stress exceeds the material strength, the material will fail. In this case, we consider the material to be free from any pre-existing cracks. Now, firstly, failure occurs when the material starts exhibiting inelastic behavior. So, when it is elastically deforming, then it will regain its initial size and shape. So, we are not worried about that part. So, we only say that material has fractured when it shows some permanent deformation. And brittle and ductile materials will be having different modes of failures, and depending on the loading, so what type of loading we are providing, it will show different type of mode of failures. In case of ductile materials, they exhibit yielding and plastic deformation before failure, while brittle materials, they show no yielding and they show a sudden type of failure. And yield stress is one of the material property that we use in case of ductile materials. Factor of safety is another part that we use. Okay, someone has joined. Okay, so factor of safety will be considering it for designing our materials. So we'll be considering applying the less stress to the material compared to the yield stress. Now failure will be different, so it can be brittle or it can be ductile type of failure. So using stress strain curves, we can define what will be termed as brittle and what will be termed as ductile. So when your percent elongation at failure is higher than 10% or so, then we'll be defining it as a ductile type of material. And if it is lesser, then we'll be saying that it is brittle type of material. Now in this case, initially this is your elastic part. So in this part, as soon as we remove this load, then the material will again following this path and will be returning to its original size. And this after this is the plastic part. So in this plastic part, we can consider this as failure of material. We can also consider this ultimate tensile strength part as failure depending on where we are using our material. And for brittle materials, this yield part and failure part is very closer, so we always assume failure fracture stress as the criteria for fracture this factor of safety. So in case of ductile materials, we'll be having well defined yield point, and factor of safety is used on yielding part. And in brittle materials, there won't be no yield point, no well defined yield point, and there will be sudden failure of material. Now in static tensile test, in general, ductile materials are limited by their shear strength and brittle materials are by their normal strength. Hence, one kind of failure theory doesn't explain all the materials, and different failure theories for these two classes are given. But before we talk about the failure theories, a proper definition of failure itself is important. So in case of ductile materials, it is the percent elongation up to fracture is more than 5%. And for many ductile materials, this number is usually around 10%. A component may be considered failed if it yields and deforms sufficiently large loading to improper functioning. So a component might fail by fracture, or both conditions are failures but the mechanisms are different. In addition, the loading can be static or dynamic. And here in these two chapters, for today and next chapter, we'll be focusing on static type of failure. Now ductile materials, they fail by fracture if loaded beyond the ultimate tensile strength, and typically the machine components made of ductile materials are considered to be failed when they yield under static loading. Now yield strength of a ductile material is much less than ultimate strength. In case of brittle materials, they fracture rather than yield, so they don't show any permanent deformation before fracture, and brittle fracture in tension is due to normal stress only, which is also shown in maximum normal stress theory. Now brittle fracture in compression is due to a combination of normal and shear stress, hence requires a different theory. And there are two type of materials as well in case of brittle. So even material will be where compressive strength is equal to their tensile strength. This is seen in wrought steel, which are brittle, but their tensile strength is equal to their compressive strength. So example of these is fully hardened tool steel, which can be brittle. Others are uneven material in which compressive strength is not equal to tensile strength. So grey cast iron is brittle and its compressive strength is much higher, around 3 to 4 times higher than the tensile strength. And the presence of microscopic flaws are there in castings. So in cast material, so these flaws act as stress concentration razors when we apply tensile type of loading. So they fail earlier in tension compared to in compression. Some cast brittle materials can have higher shear strength than their tensile strength as well. And shear strength of the, yeah,
Excuse me, ma'am, if we have a flaw,
yeah.
so is it necessary that only in case of tensile loading it will act as a stress concentrator, like compressive stress if we apply, then will it act as a stress concentrator still?
No, see here you can see right below pointer, these are crack type of geometries. So if I'm applying compressive type of load, right, then it will act as like cold welding type of phenomena, right? I'm compressing it from the both edges. So these cracks will try to get shut in that case rather than opening. And when I am applying this tensile type of loading, then these cracks will further open and crack propagation will is more likely to take place when I am applying tensile type of loading.
Ma'am, so like in that case, I'm not able to differentiate between even and uneven brittle materials. Like in that case, all the brittle materials should be uneven.
No, as shown here, like in case of your road type of materials, there won't be this presence of these microscopic flows. In that case, this tensile strength and compressive strength both will be equal. That will be your
Okay, okay,
even
okay, okay,
material.
okay, 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 ma'am, okay, ma'am. Yes,
Yeah.
ma'am.
Okay. Now shear strength can also be different in some materials, and it is half of the tensile strength. Now ductile steel specimen fail in shear. Since torsion is the pure shear loading, the failure is along the maximum shear plane. Now brittle cast iron specimens fail along 45-degree plane to the specimen axis, as the failure is along the planes of maximum normal stress, as the material is weak in tension. Now this uneven type of effect can also be in ductile materials. So some metals also show the uneven response of yielding. So some wrought magnesium alloys have compressive yield strength equal to 60 to 70% of their tensile yield strength. Now why we need for a failure theory? So sometimes when we are applying different type of loading, so there can be uniaxial type of loading, biaxial type of, or triaxial type of loadings. So they will give different type of properties of materials. So as we saw earlier, it will be showing different compressive strength compared to tensile strength. So for defining these, we require different type of theories for different type of materials. So in these theories, what we assume that there is no crack present. So, and this material is isotropic in nature and homogeneous at entire region. Now general form of failure criteria. So here the resistance of a material to yielding is given by yield strength. So to apply fracture criteria, we use ultimate tensile strength in case of ductile materials. And the failure criteria for isotropic materials can be expressed in the form of F function of sigma 1, sigma 2 and sigma 3 as equal to sigma c at failure. So this entire stress, it will lead to failure stress at the failure depending on material. Yield and ultimate will be using depending on material, whether it's ductile or brittle. Now why the failure criteria written in principal stress space? So a valid failure criteria should result in the same outcome independent of choice of the coordinate system. Hence the functional form of F could also be in terms of invariants of the stress tensor. When plotted in principal stress space, the function F indicates a surface called failure surface, which will be either yield surface or fracture surface. So your different failure theories are basically different choices for mathematical form of function F. Engineers tend to choose the mathematical form that matches closely with the experiments. Okay, for ductile materials, there are various failure theories that are given. Maximum normal stress theory. So in these theories, we define based on which property your material will fail. For example, in this maximum normal stress theory, will be focusing on principal stress, and in case of maximum normal strain theory, here we'll be focusing on strain and total strain energy. So here we'll be focusing on strain energy. These all are defined for ductile materials. Distortion energy theory, which is given by von Mises, and maximum shear stress theory given by Tresca and Guest. So these last two theories, which are in bold letters, these agree much with the experimental observations. These are older theories which are relatively less used. Now, design conditions for various failure theories. So in case of maximum principal stress theory given by Rankine, so here condition for design is sigma 1 should be less or equals to sigma your can be your yield stress, or your principal stress should be less or equals to your UTS or yield stress depending on material type. In case of maximum principal strain theory, 1 upon E times sigma 1 minus mu sigma 2. So here strain is used, so we are dividing it with elastic modulus. In maximum shear stress, again here sigma 1 minus sigma 2, so two principal stresses are used. And in case of strain energy theory, we are using strain energy, so it is in terms of square, and capital E is in divide, so that is cancelled from both sides. In case of distortion energy theory, we are using sigma 1 square. This is again energy, so it is in terms of sigma square. Now, when one of the principal stresses at a point is large in comparison to the other, all failure theories gives nearly the same result. And when we use uniaxial type of tension loading, then also these all theories will give similar results. Now, stress state at a point in material. So when we are applying stress to a material, there are various points in this material we can consider. Now, if I am considering this point and this to be a cube, then how this stress will be acting on this point. So this stress state can be given in terms of a second order of tensor quantity, which will be a 3 by 3 matrix. Now here 9 components of stress tensor will be there. So this is your sigma yy, sigma xx, sigma zz. So here x tau is your stress, x is your denoting your direction in which we are applying stress, y is your plane, normal plane according to here. So here sigma yy, so y is the direction as well as this y plane. And in case of xx, this is your principal stresses where both are x, both are y and both are z, and others are shear stresses. Now first is von Mises distortion energy theory. So in this case, your strain energy up to yield point is considered to be to decide whether your material is failing or not. So in this case, microscopic yielding is due to relative sliding of atoms within their lattice structures. So this sliding is caused by shear stress, dislocation motion accompanied by distortion of shape of the part. Now energy stored in material from the distortion is an indicator of shear stress present. And previously, as we used to study, total strain energy stored in material, it causes yield failure. But experiments have shown that this is wrong compared to that. Now total strain energy density, here we assume linear stress strain up to yield point. So this strain energy, which is resilience, we always calculate it by half sigma times E. So this is a triangle. So E is your strain, sigma is your stress, and half for getting area of this triangle. So this is the energy stored up to that point. Now this energy is stored now in 3-dimensional using principal stresses and strains. We can write this in terms of 3 dimensions. So sigma 1, sigma 2 and sigma 3. And E is your 3 strains in 3 directions. Now E is written in terms of sigma. So by using formula in terms of Poisson's ratio, we can write this entire equation in this form. Now, as I told earlier, hydrostatic type of loading. So, a very large amount of energy can be stored in a material without failure if it is of hydrostatic type of loading. This is possible because the creation of a uniform stress state in all directions. So, materials can be hydrostatically stressed beyond ultimate strength in compression. Now, P.W. Bridgman, he subjected ice to 1 mega of pounds per square inch of hydrostatic compression with no failure. So, according to this hypothesis, uniform stress in all direction creates only volume change but no distortion. And in case of Morse circle, that will be studying in next chapter, for hydrostatic state it is a point, so there wouldn't be any distortion related to hydrostatic type of loading. Now, as we can write this formula in this form, after this, to check for failure, we compare the distortion energy per unit volume above the equation with the distortion energy per unit volume in tensile test specimen at failure. So, when we term it in terms of uniaxial tension, then only one value will be there for principal stress, and sigma 2 and sigma 3 will be 0. So we can write in terms of uniaxial as 1 plus mu divided by 3e upon sigma square y. Now this equation, when we compare it with initial equation, then we can say that sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 1 sigma 3 whole square root should be less than sigma y. This is your von Mises criteria. Now for the case of pure shear, in this case your sigma 1 will be equals to tau equals to minus sigma 3 and sigma 2 will be 0. Now putting all these values, you will be getting that sigma 1 should be equals to sigma y upon root 3. So your this shear type of stress, that will be 0.577 times the sigma y in tensile tension. So shear yield strength of a ductile material is 0.5, means half times the tensile yield strength. So the ductile failure from distortion energy theory. So failure in case of ductile material is in static tensile loading is considered to be due to shear stress. Distortion energy theory. So in this, the statement, as I told earlier, this is the statement for this theory. And in case of two dimensions, sigma 2 will be 0 and you can write sigma y equals to under root sigma 1 square plus sigma 3 square minus sigma 1 sigma 3, which is an equation of ellipse if you make it square here. Now which state of stress is likely to cause yielding? So I think you got this type of question in this assignment as well. So in this case, these both are almost similar, just addition of one and hydrostatic state is there. So if I add 10 10 10 in all these principal stresses, then I can get this stress state. So both will represent an equivalent state of stress corresponding to yielding, as the second stress state is only an addition to the hydrostatic stress to the first one, which doesn't contribute to distortion.
Ma'am,
Yeah.
can you the previous slide, like that formula of von Mises, if we apply
Yeah.
here,
Yeah.
then like ma'am, see, sigma 1 and sigma 2 and sigma 3, although
Hmm.
we are adding constant values,
Hmm.
but like their magnitudes are different, no ma'am. So the sigma y which we will get in both the cases will be different. So how they are equivalent?
Okay, so you calculated for both of these, right?
Yeah, yes, ma'am. For both of them, if we check it, then like in one I have
Hmm.
10, 5, and 5. In another I have 20, 15, and 15.
Yeah.
So if sigma 1, sigma 2, sigma 3 values accordingly I will take and I will apply in the formula, then the value of sigma y will be coming different in both the cases, no ma'am?
Yeah, yeah. But here, as he stated, right? According to Bridgman, these all. So they are applying just hydrostatic type of compression loading. Then only volume change will be given. So even if it is even going further than your ultimate strength, it can be stressed beyond ultimate strength. And here you are just considering your yield strength. So these all theories won't be true for all the cases.
Okay, ma'am.
Okay, now the von Mises effective stress is defined as the uniaxial tensile stress that would create the same distortion energy as is created by the actual combination of applied stresses. Now, sigma E is given as effective stress. Now, if we divide sigma Y upon sigma E, you can get your vector of safety. So, this sigma E should be comparatively lower than your yield stress. So this is how you define your factor of safety. Now maximum shear stress theory, Streska Guest theory. So this was first proposed by Coulomb and later by Tresca followed by J. Guest. Now their statement is failure occurs when the maximum shear stress is a part exceeds the shear stress in a tensile specimen at yield. So 1/2 of the tensile strength. So this says sigma ys equals to 0.5 sigma y. So your shear stress is equals to half of the yield stress. So for a general loading case, if we are taking two principal stresses, sigma 1, sigma 3, so these are 3. So sigma 1 should be highest and sigma 3 should be lowest. These are three principal stresses. So we can use minimum and maximum only, and we can get what will be your maximum shear stress. Now based on this shear stress, this this equation should be higher than your yield stress. Now maximum normal stress theory, in this only, this is historical theory, so it is a lot, this was suggested a lot prior to these comparatively newer theories. It is not safe to use for the ductile materials. Now the failure occurs when the normal stress in the specimen reaches tensile yield strength or ultimate tensile strength of material. While we know that when we are applying certain stress to the material, certain planes are oriented preferably to the comparative, they are more likely to undergo some shear stress earlier compared to when it reaches its yield strength or ultimate strength. And Tresca and von Mises theories, so these two theories, in these as well, we see that when we see for aluminium, mild steel and copper, these ductile materials, these are show more agreement to the von Mises theory compared to Tresca theory. So it is experimental data shows good agreement with von Mises theory, which works on strain energy theory compared to maximum shear stress in case of Tresca. Tresca is conservative compared to von Mises, and von Mises theory is more accurate and generally used in designs. Now experiments show that for ductile materials, yield in shear is zero point 0.5 to 0.6 times of yield in tensile. And that's all from my side. I'll repeat the questions again for those who joined later. Okay, any query? Uh, okay, so first question was what doesn't act as notch? Your options were groove, smooth contour, hole, fillet. Answer was smooth contour. So these smooth areas, these don't provide any stress concentration compared to these other folds in specimens such as groove, hole, fillet, etc. And these abrupt change in cross section, these all can lead to formation of stress concentration points leading to formation of crack initiation. Second question is to apply fracture criteria, blank is used. Your options are fracture strength, ultimate tensile strength, yield strength, or creep strength. So in fracture criteria, ultimate tensile strength is used. And the resistance to material is yielding, which is given by yield strength. In fracture criteria we use UTS, and fracture fatigue strength is used for cyclically loading parts, and creep strength is when we provide some temperature to the material as well. At certain point in a structural member, there are perpendicular stresses 80 Newton per mm square and 20 Newton per mm square, both tensile. What is the equivalent stress in simple tension according to maximum principal strain theory? So in this case you are given Poisson's ratio. So this formula you have to use. You equivalent strain. So here equivalent strain equals to E1. E1 is your sigma 1 upon capital E minus mu upon sigma 2 upon capital E. E will be, both sides have E, so you will be remaining with sigma equivalent equal to 80 minus 0.25 times 20, which will be 75 MPa. Now in Hall-Page model, hardness increases with reduction in grain size because grain boundaries. They act as either source of dislocations, aid dislocation motion, act as barrier to dislocation motion, or act as sinks for dislocations. So your answer will be they act as barrier, which leads to improvement in hardness and tensile strength. So in fine grained materials, that's why they show harder and stronger compared to coarse grained materials. Fifth question is the maximum distortion energy theory is suitable for which type of materials? So your options are ceramics, ductile metals, composites, polymers, and it will be for ductile materials. And maximum strain energy theory doesn't work for brittle materials because they have different elastic limit in compression and tension, and according to this theory a body complex strain stress fails when the total strain energy at the elastic limit is in simple tension. This is the graphical representation. Which theory is suitable for brittle materials? Options are maximum principal stress theory, maximum shear stress theory, total strain energy theory, maximum distortion energy theory. Answer will be maximum principal stress theory. So in case of brittle materials, we don't consider strain and energy, distortion energy, strain energy theories. These are for brittle materials. So for brittle materials, principal stress theory is used, maximum shear stress theory, strain energy theory, maximum distortion are used for ductile materials, and Tresca theory fails in the hydrostatic state of stresses. And all theories give same type of results when we load them uniaxially. Now in this question you are given two stress states. One is addition to the hydrostatic state. So 555 is added here. So this won't be contributing to your distortion of the material. So this won't be leading to any failure of material. So these two stresses, they are more equally probable for yielding. Second stress state, in the addition to a hydrostatic stress state to the first, so both sigma 1 and sigma 2 are equally probable for yielding. Question 8. The uniaxial yield stress of a material is 866 MPa. According to von Mises criteria, the shear yield stress of the material is. So according to von Mises criteria, when we load our material uniaxially, this is your equation that you use. Tau equal to sigma y upon root 3. Sigma y is your yield stress, 866 upon root 3, which will be 500 MPa. Now, what is the shape of the total strain energy theory? So, these are various shapes that are given based on the equations of these theories. So, there will be ellipse in case of total strain energy theory and in case of maximum distortion energy theory. Elastic limit of cast iron as compared to the ultimate breaking strength point is, options are half, double, thrice, same. So in case of elastic limit cast iron type of brittle materials, your stress strain curve will look like this, and so there will be very less plastic deformation part. So these two will be almost same, elastic limit and your ultimate breaking strength. Now that's all from my side. If you have any query, you can ask. I'll be here till 5.
Ma'am, those assignment questions won't be discussed.
Which assignment questions?
Ma'am, that this course week 5 assignment questions.
Those I can discuss. That those you have to solve, right? After
Yeah, yes,
their,
ma'am.
yeah, after their answers have revealed, after that I can tell you if there is some query after that, if you got that wrong or something.
Okay, 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 ma'am. Okay, ma'am. Ma'am, like in general, we design failure theories for brittle materials and ductile materials. Like suppose if we have a composite, let's say a metal matrix composite.
Yeah.
So in that case, how do we design a theory?
Okay. Okay, there is, yeah, we design composites because we want to get advantages of both, right? Ductile materials and your brittle materials. So for those, these theories won't be used because they are combination of both. So most of theories, I don't think so these will be applied to your composites, because we,
Ma'am, then like for yeah, sorry, ma'am, continue.
yeah, when we, for example, when we want to measure what is its elastic modulus or that, so we use some addition rule, right, in composites. So based on that we can decide like where, at which particular point it will fail or like that. So I don't think these theories will be applied to composites, or I'll check.
Okay,
Yeah, I'll check
yeah.
if,
Ma'am, like in general, I'm asking like because all the theories that I have heard till now, they are mainly designed only for, let's say, a brittle or a ductile material. But like when we are designing composites, then let's say, suppose if we are checking the strength of fibers, okay, whether the fibers will fail or whether the matrix will yield or not. But like, as a whole, composite as a whole, like, is there any theory which exists?
No, these theories are not for composites, that's for sure.
Okay, okay, okay.